Welcome back to Cartoon Physics. In the previous episode, we saw what would happen to Antman's initial acceleration if his mass remained unchanged when he ballooned into Giant Man. His initial acceleration would be unthinkably high, but what does that mean for his top speed? In this episode, we'll calculate his terminal velocity based on the buoyant force, the drag force, and the force due to gravity. We'll use some standard values for a drag coefficient, the density of air, and a value to estimate Antman's cross-sectional area as Giant Man. We'll start off with a free body diagram showing the forces: the buoyant force going up, the force due to gravity going down, and a drag force which always opposes the direction of motion. Drag forces are based on the density of air, velocity squared, a drag coefficient, and a cross-sectional area. A drag coefficient of 0.7 is common for skydivers going headfirst, as is a cross-sectional area of 0.18 meters squared. Notice that we're scaling this by our scaling factor that we found in the first video, and we have to square it because area is a two-dimensional term. We also have the density of air, and we have volume of 4,155 meters cubed. This is Antman's giant volume that we found in the previous video. The next step is summing the forces and setting them equal to 0. When the forces are equal to 0, there's no acceleration, and this is the definition of terminal velocity. We want the force due to drag isolated on the right side, because this is the only term that has velocity. We'll rewrite the equation symbolically, and the next step is solving for v. We'll multiply both sides by 2, divide by rho, put the drag coefficient and area in the denominator, and then square root the whole thing. This is our symbolic expression for terminal velocity. The next step is plugging in our values. Don't forget the square root. And now we can solve for our terminal velocity. So, Antman's terminal velocity is 22.4 meters per second. This is about 50 miles per hour, which is a speed we can wrap our heads around, even though his initial acceleration was huge. This goes hand in hand with an assumption we've made, which is that he gets up to his terminal velocity pretty quickly. If this weren't the case, then air density would change as he goes up into the atmosphere. And speaking of that, in the next video, we're going to find out what his maximum height is. Thanks for watching Cartoon Physics.